Welcome to this explainer. Today, we are blasting right off the surface of the Earth to look into one of the absolute most mind-bending concepts in astrophysics. We're talking about gravitational potential. So let's just jump right in.
Okay, so you probably remember the classic equation from high school physics, right? Potential energy equals mgh, mass times gravity times height. It's perfect for when you're dropping an apple or analyzing a roller coaster. But here is the big question. Does this trusty everyday equation actually hold up when we get out into deep space? Well, let's see where it completely breaks down.
See, near Earth's surface, gravity is essentially constant. It doesn't really change, making the math super easy. But as we travel out into deep space, gravity actually weakens pretty rapidly. It drops off exponentially the further away we get. Because that gravitational force is constantly changing, our standard mgh equation, it becomes completely invalid. Just literally useless out there. I absolutely love this insight, taken directly from some handwritten student notes in our source material. It says, "We take work done in segments because the force of attraction is changing." And man, that really hits the nail on the head. That is the exact crux of our problem. You just can't use one sweeping, easy calculation to figure out energy if the gravitational pull is shifting with every single meter you travel. So to solve this, physicists kind of have to rethink the whole journey. Instead of calculating the entire trip all at once, we slice the distance from the Earth all the way out to infinity into these tiny, discrete intervals. They're labeled here as delta R. We actually make these steps so incredibly small that the force of gravity within each individual segment remains, for all intents and purposes, completely constant. It's like slicing up a giant puzzle.
And this breaks some pretty intense calculus down into 3 highly digestible steps. Step 1, you divide the total distance into those tiny intervals. Step 2, you calculate the work done for just that one specific constant segment. And step 3, you simply add up all those individual bits of work. It is such an elegant way to bypass the whole problem of a changing force. But here's the catch. To actually sum up the total energy across these millions of tiny segments, we desperately need a starting line, right? We need what's called a zero reference point. Like, if you're measuring the height of a mountain, your baseline is always sea level. But for cosmic gravitational potential, where in the world do we set our zero point? Is it Earth's surface? The center of the Earth?
Well, to make the math work universally, we need a massive paradigm shift. We do not start at the Earth's surface. Actually, we establish our zero reference point at infinity. I know, it sounds crazy, but mathematically, it's literally the only stable, universal baseline we have available to us. We basically have to count backward from an infinite distance.
So, why infinity? Why way out there? Because at an infinite distance, the Earth's gravitational pull has finally faded to absolutely zero. By setting potential energy at infinity to exactly zero, we get this universally agreed-upon clean slate. And suddenly, the math becomes beautifully simple. Okay, let's just trace this logic for a second. If an object is at infinity, its potential energy is zero, period. As objects move apart, they have to work against gravity, so their potential energy increases towards zero. But what about falling from infinity toward Earth? Well, in that case, gravity is doing the work. You lose potential energy. So if you're starting at zero and decreasing, your gravitational potential energy has to become negative. No way around it.
And if you look closely, the actual textbook derivation confirms this exact logical deduction. When you add up all those tiny segments of work we talked about, notice that crucial little negative sign right at the front of the result. Because our zero point is at an infinite distance, potential energy anywhere closer to Earth is fundamentally a negative value. We are literally always living in a gravitational energy debt.
And that brings us to our true cosmic equation. Absolute gravitational potential energy, or U, equals negative g times the mass of the Earth times the mass of the object, all divided by r, which is the distance between them. This perfectly, seamlessly models energy on a massive scale, fully accounting for that weakening force of gravity over vast, vast distances.
So we've completely changed how we view energy in space. Any objects in orbit is basically trapped in this massive negative energy well. Which brings us to a really fascinating final thought. Think about this. If a satellite's potential energy is fundamentally negative, what massive amount of kinetic energy does it actually take to climb out of that hole, reach zero at infinity, and escape Earth's gravity entirely? Well, that right there is the secret behind escape velocity. I highly encourage you to keep exploring that concept. Thanks so much for joining me on